Hi everyone, I'm Nicolas Pita, a PhD student from the Model Force group, and welcome today to the video tutorial, which is part of a series of tutorials of how to do CFD simulations on left ventricles. And well, today particularly, we're going to work on the simulation setup for the Star-CCM commercial solver, which we use on our group to do some of the simulations. And well, if you haven't seen the previous video about geometric preprocessing, in this video we're going to use some of the things that we created and said in the previous video. So if you haven't seen it, maybe you have to go back and see this video. But well, let's start. As I said, today we're going to talk about the tutorial of Star-CCM. And as a previous point before starting to the setup on Star-CCM, we need this MATLAB software to run a script to create the necessary files. Then, of course, a Star-CCM solver. And as I said, the STL files that we generated in the previous video, where here we're going to use the minimum and the maximum volume, particularly. Then, also, you can download and use the .sim file that we will give, where the setup of this tutorial will be done, and you can follow this tutorial better. But we're going to start from scratch, so you can also follow it and start from scratch your simulation. And finally, before starting, we're going to, as I said, run these create necessary files in MATLAB, so we can create the initial scaled mesh if it's necessary. If you have your mesh scaled, this will not be necessary. And also the tables that we need for the boundary conditions, such as inlet, outlet, or the most important one, which will be the wall movement. So let's go then to MATLAB, and in this script, if we start from the beginning, we will create the workbench as always, and then start by loading the STL files, as I said, from the minimum and the maximum volume. That would be the end-system volume and the end-diastole volume. Here, you will need to modify for your own geometry or your own time steps or whatever. In our case, the maximum volume is for the adimensional time 0.67 of the cycle. Then, as I said, if you have it scaled, that's perfect. In our case, our data is in millimeters, and we want it in meters, because this code is in meters. So we do the scaling here for both data points, for the minimum and the maximum volume. So if we run this, we will get the following. As you can see, in red we have the maximum volume, and in black we have the minimum volume. And well, if we follow the code, and here we are going to export the initial and the final mesh. For in our simulation, we will just need the minimum one by scale. So this would be the necessary, but well, you can also export the maximum one. And again, if you have it already scaled, you don't need to do this. You can remove that. And then this is an important part of the code, because here we're going to calculate the displacements of between the minimum and the maximum volume, and create a table together with the points that we have from the maximum volume. So you can see that we will have in the first three columns the displacement of each point of the left ventricle from the minimum to the maximum volume, and then in the next three columns the three directions, the x, y, z points for the maximum volume. This, as I said, it's really important for our simulation, so we can use it to define the wall movement. And here what we're going to do is export this as a table, as a CSV file. So if we run this, we'll create this table. And well, now this part is a repeated part from the previous tutorial of geometry preprocessing. So I'm going to go fast. If you have any doubt, you can go to the video. But there is a really important thing here that we have to, that is for the rest of the script also, which is defining the number of time steps for the profiles has to match with the number of time steps in your simulation. So if at any point you change your simulation time step to have, for example, 2000 time steps, then you have to also rerun this and reload the tables that we're going to create. So well, we have defined this time step as 1000, and then here what we are going to do is compute. Well, let first load, interpolate, and correct the flow rate chart, which we have of the flow going in and out from the left ventricle, and then integrate it so we get the volume variation here, the integration of the flow rate chart to get the volume variation of the left ventricle. So if we run this section, we will get two new graphs, which will be the flow rate chart here with its interpolation and the volume variation chart, where you can see how the volume changes throughout the cycle. So once we have run this, then we just have to we'll finish by exporting the boundary conditions. So first, we are going to export the incremental volume variation. For that, we are going to normalize the volume variation and then calculate the incremental for this volume variation. So we can use it as boundary condition for the world movement also. And then both the inlet and outlet condition, we can also export it from the flow rate chart and create the tables necessary for introducing this to our simulation. Sorry. So if we run this, we will create the three tables of incremental volume variation, inlet velocity, and outlet flow rate, for example. And well, it's important, as I said, to define the number of time steps. So the table will have these time steps defined. And so well, be careful with that. So now that we have finished this, we can go back to the slides and start defining our simulation on Star-CCM. So well, once we have the necessary files, we are going to open Star-CCM, start a new simulation, or open the one that we provide. And well, the first step, of course, would be to load the geometry. Throughout the tutorial of Star-CCM, we will have many steps, and I'm going to go in the software itself step by step, but in the PowerPoint, I'm going to go a little bit faster. So in the end, to load the geometry, we need to enter the 3D CAD models, import the geometry, and then once we have imported it, we are going to repair the surface by, well, create the geometry part from the CAD, and then we're going to repair the surface and declare the different boundaries, such as the inlet, the outlet, and the wall. So for that, we're going to go to Star-CCM, and as I said, we're going to create a new CAD, which will take us to this other window. And here we are going to select import and select our end system volume, the scaled version of our end system volume. Therefore, we're going to load the minimum volume here, as you can see. And once we have this, we will just close the 3D CAD. And we will see that here, now we have a body group called MATLAB. In my case, because I created it from MATLAB, in your case, it can have another name. So we are going to create from here, create a new geometry part. Okay, we click OK. And then you will see that here we have created another part. So I'm going to go renaming it so we don't lose track of each thing. This will be our ventricle. And as you can see now, we only have the default surface. We can also create here a scene, so we can see of the mesh, so we can see the geometry itself in this screen. And well, as you can see, we have the STL file here. And what we want to get now is the inlet, outlet, and the wall boundaries separated, because right now the whole surface is one. So for that, we're going to click in Ventricle, repair surface, OK, from the root. And we're going to enter this another window, which is edit. And here, as we only want to, of course, if you have any holes, steel, or whatever, here you may be able to edit it. But in our case, we just want to select the boundaries. So for that, we are going to double click in the inlet. If they're in the same plane, it will auto select it with the double click. If it's not the same plane, which would be strange, but well, it can be, you would have to select manually or use another tool of growth from a layer, surface or whatever to obtain this. But well, in our case, with the double click, we have it. We'll right click on this surface and select part surfaces, modify to new. And here we will put new part surface inlet. The same goes for the outlet. Double click there, part surface, modify to new, outlet. And what we also can do is select both of them and invert selection to take the wall boundary, and again modify to new, part surface, wall. So now we have already declared the three boundaries. If we close this, we will see that now in our part, in our ventricle, we'll have our inlet, our outlet, and our wall. So we can already get rid of this. And that's it for the geometry section. That would be the most relevant things to do. So well, let's go back to the PowerPoint. So as you can see, we already have done all of this. So we can skip to the simulation setup. And well, in other softwares or solvers, now would be the step of doing the meshing. But in Star-CCM, we first need to create a region associated to our geometry part, and well, also as we want to introduce wall movement in our simulations, we have to first also define this wall movement or this boundary condition, and then we will do the meshing. So the meshing would be the last thing before the initialization of the solution. So to create the region, first, the previous step would be to create the continua, which is to specify the physics of our simulation. And for that, we're going to create a new physics continuum. We're going to rename it as blood, since it's what we're trying to model, the blood inside a left ventricle. And well, the different models will be three-dimensional, liquid, acids and incompressible flow, constant density, laminar, etc. So after we have declared this continua, we're going to create a region from associated to our geometry part. And inside the region, we're going to also create the boundaries and associated to each surface we have declared, such as the inlet, the outlet, and the wall. After this, we're going to introduce the data tables of the different boundary conditions we have created in the MATLAB script. Then we're going to create the field functions, or in the case of the incremental volume variation, the report for interpolating the table inside the Star-CCM. And well, finally, in this section, we will define the inlet and outlet boundary conditions by creating the appropriate field functions, and also introducing it to the boundary itself. So well, let's go again to Star-CCM. And well, here We're going to close already the part of geometry. We're going to go back to the when we mesh it, but now for now, well, not truly. So first we said that we need to create the new physics continuum, and here when we select the models with the right click, we'll have here the different models we are going to introduce in our simulation. So first we did three-dimensional, as our ventricle is three-dimensional, liquid, since we're trying to model blood. We also said coupled flow, constant density, implicit and steady, laminar, and well, we can also add other things such as the wall distance, the solution interpolation, and I think that's all. So, well, if anything is missing, you can check the department. I think those are the things we need to declare. So we can rename this as blood, that you will see that it's in blue because it's liquid. And so here we can also define many things. For example, we want implicit second order in our coupled flow. In liquid, here it's not water, it will be blood, and we are going to change then the value of the density of our constant density, which is 1060, and the dynamic viscosity, which would be 0.004. So there we go. And well, nothing else, everything as default, but here you can change other things of the model. If you need also to change something about the reference value, such as the reference pressure, which in our case is one atmosphere, but well, here you would have it, and then we're going to go back here for the initial conditions when we see the initialization. But well, let's now go to the geometry part, and as I said, to associate this to the region, we can just create the region, but we can also from here create a set new region, and we will call it ventricle. So if you check now here, we will have a new region called ventricle, and in the boundaries we will just have one default one, which we can, for example, call it wall, since it's already declared as wall. We'll also create a new one, which would be our inlet, and for this we're going to have to change this to velocity inlet here on type. You can see, we can see that the figure is already changed, and here in the part surfaces we're going to check the inlet. And now a new boundary, which will be outlet, and again we're going to change the type of this to outlet. In our case, we're going to select outlet. You can see that it's already selected, and in wall you can see that it's a wall with ventricle wall. We're going to go back afterwards to see this physics value and physics conditions when we declare the velocity inlet and so on. But right now we're going to go to import the tables to introduce the profiles that we want to use as velocity inlet and mass flow outlet. So for that, we're going to go to tools. We're going to right click in tables here down, new table, and file table. In our case, we're going to put all of the tables that we extracted with the MATLAB script. And you can see here that we have now loaded all of these tables. And then the next step would be to interpolate these tables so we can use it as profiles in our boundary conditions or expressions or whatever. So we're going to declare a scalar that we will call inlet velocity, And here we can also call this inlet velocity, so we can use it afterwards. And another thing we have to prepare here is the dimensions. You can declare here, this is velocity, would be meters per second, so 1 in length and -1 in time. Or down here you can also check this to 1. In both cases it's the same. You have to be careful of the units here, but we can leave it as that, meter per second. Then we will create a new scalar, which will be the outlet, and flow rate. Let's call it that. Again here, the name, so we can call it from other functions. And in this case, we will have volume, so 3 lengths times per second, which will be times. So we will have this. And now we have to declare the definition of these field functions, which in the case of the velocity, we will take the table and of the inlet velocity and interpolate it. So we will write this expression of interpolate table periodic. Inlet velocity, in our case, right now is with this time step, which we created. And sorry, so that should be correct. So here we have our table, the first column, which is called T, use linear for the interpolation, Belling, which is our second column, and then do the periodic interpolation with 1 as our period. And well, with this we can introduce the velocity inlet, and we'll do something similar for the outlet, where will we call this outlet flow rate dt. Instead of Belling, we will have our out, and the rest is the same. So now we have introduced those tables. The next thing would be to do something similar, but instead of being a field function, it's a report. So we are going to go to reports, new, and in user, we're going to introduce an expression. And again, the definition, it will be the same. It will be the one that interpolate the table periodic using the table we have. So here would be the incremental volume, TD ball, and everything else is the same. And we will call this displacement interpolation. So well, right now we will have all the data tables imported, and the next thing would be to create some parameters and field functions, so we can generate our functions for introducing it in the inlet and the outlet boundary conditions. So for that, we're going to go again to field functions. There will be also 2 scalars, and we can call this, well, we could introduce this inlet velocity directly to our boundary condition, but in our case, we want to use you can use, if you want to use some kind of spatial profile, such as parabolic profile or whatever. In our case, we'll want to introduce, as we have used this in our simulations, the hyperbolic tangent profile. So we will call this also inlet velocity hyperbolic tangent. Again, this will be time length -1 in time, meters per second. And in the expression, we will introduce the following thing. So, as you can see, if we want to introduce our inlet or the radial coordinate of the inlet, we'll have to also create them. If else, they will be in red. So again, we're going to create the radial coordinate. So inlet radial coordinate. This will be just length, and the expression is just the square root, the square root of the x, positioning it well in our inlet, and the square of the vertical direction. And well, if we want to define some parameters, we're going to go here, scalar, and the parameters we needed were the center where the inlet is located, which in our case is 0.06 negative, but well, that we will take into account afterwards. And another parameter which would be the value will be this thing, and this will be the inlet radius. So R inlet, our inlet. So now if we go again to our field functions, we can see that the inlet radial coordinate, which I didn't save well, it looks like. So now, yes, now we can define this. And here we will also everything have in green, since now we have declared everything. And now we have already the profile, the spatial and temporal profile inside this field function for the inlet. And we are going to do something similar for the outlet. In our case, we're going to introduce our outlet flow rate as mass flow rate. So for that, we just need to, again, outlet in this case will be mass per time, and the expression will be what we have in outlet flow rate times the density. So that way we have our mass flow rate. So now we have defined all of the profiles we need for the boundary conditions. So we're going to go back to this to the regions, and here for the outlet, our mass flow specification will be mass flow rate, as I said earlier, and here we will have to declare our field function, which will be outlet mass flow rate. Take care that it's the mass flow rate, not just the flow rate. And then for the inlet, the velocity specification and all should be good, but you can check it here. But in the end, what we want to introduce here is the velocity magnitude, which in our case is the inlet velocity hyperbolic tangent. So with this, we can close this section where we have declared the region and the boundary conditions for the inlet and the outlet. So now we can see that our part ventricle is linked to the region ventricle we have just created here. So well, let's go back to the PowerPoint and start seeing the next section, which is how to declare the moving wall. So, well, as we said, we need to specify also the motion of the wall, since our left ventricle wall will be moving in our simulation. And for that, we're going to use the morphing tool implemented in Star-CCM. And also, before continuing, even though we're going to do the principal meshing afterwards, we also need to at least add the operation of automated mesh to our geometry part, and select these three methods and just mesh, so we can detect with our data mapper, that is the next step we're going to do in the moving wall, we can detect the mesh. But as I said, we're going to come back to meshing because we're going to refine it. But in the first step, in just running the mesh here, creating the mesh is necessary for us to go forward. Then, depending on if you have an idealized case or a patient-specific one, we are going to map the data differently. For example, in our case that we're going to apply the wall movement to an idealized case where we know the analytical expression of the wall movement, we are going to use the function data mapper or the surface data mapper, introducing a field function which will be the displacement vector. And for that, we will create some parameters and create some displacement functions. And with this, create the displacement vector that we are going to use in our data mapper for our surface data mapper. For an ideal case, and if you know the analytical expression of the wall movement, this is the best thing to do because it's more accurate. But in the case we are using a patient-specific one and we just have the evolution of the wall but not the analytical expression, then we're going to use the tabular data mapper, and in that case we are going to use the created table in the beginning when using the MATLAB script, introduce it, and specify the displacement as the source data. So once we have created the data mappers, we are going to map this data depending on which geometry or case we are, and also the entry to the morpher or to our morphing method here. Then we're going to create the mesh movement by creating some monitors that monitor the movement of the mesh, and we're going to use this as an input to mesh operation that we're going to specify later. And finally, we are going to prepare the moving wall boundary by introducing this morpher entry in our wall boundary and specifying that the wall is moving. So we go now to Star-CCM. As I said, we'll have to specify the motion, and for that we're going to go here in Tools, to Motions, New, and Morphing is the method we're going to use. Also, in our case, it's region-wise, but instead of B-spline, we're going to use RBF method. So once we have created this motion, the next step, as I said, would be to go to the geometry and create the operation of mesh, automated mesh. It is going to open this window where we have to select our geometry part, which has to be associated to the region, then surface remeasure, tetrahedral remeasure, and also I'm going to include prism layer measure, since afterwards we're going to use it. But well, for now, with the thing it created, just change the base size, because in our case the ventricle is way smaller than this. I'm going to put one to the 10 to the minus 3, and then we're going to generate mesh by here, generate volume mesh. So once we have done this, we are going to be able to detect it in our data mapper. So we're going to close this and go again to the next step, which is creating the data mapper. As I said, we have two options. As our geometry is ideal, we are going to introduce a surface data mapper. And for that, we have to specify the source, which will be in our case ventricle wall. But before continuing, we also need to specify some field functions and some parameters, as I said. In this case, for not taking it too long, I have already uploaded the different parameters needed. Also the field functions. To know what we introduce in each one, you can go to the slides, and there you have all the expression written. But as you can see, we have two coordinates, the angular and the radial, for the ventricle. And then we have the displacement radial, displacement vertical, and finally the displacement vector, which we're going to introduce in our data mapper. So going back to the data mapper, here, as I said, we're going to introduce the displacement vector as in the source field function. And then if we go again to surface here inside, we have to target the entities, which will be again the ventricle wall. And that's all. You can also specify more things here, but in our case, we leave it at default and this works well. And as I said, the other option would be, I will do it here, even though it's not what we're going to use afterwards. We can create a tabular data and here specify the table we're going to use. And as source data, we select these three displacements. And here again, we have to target the surface, which will be the ventricle wall, and that would be all. But as I said, right now we're not going to use this. We're just going to use the surface data mapper, since we know the analytical expression of the movement. So for that, as I said, we have to map the data, and now we have to create the field functions to introduce to the morpher and also to the mesh operation. So for that, I'm going to create the vector morpher entry. We're going to use the same name, and of course this is length, and would be the expression would be the displacement vector, the displacement interpolation that we created, the report we created before, and the mapped vertex displacement vector, which in our case has been created from the surface data mapper. In the case of the tabular data mapper, we will have three different parameters of map vertex displacement, but well, in this case, it's just a vector. So we created that, and as I said, the next step would be to create the monitors, and from the monitors, create the surface morph surface mesh entry, which we use as the entry to a mesh operation. So for that, we're going to use field sum, and we will create sum displacement x displacement x. We have to create this for the three directions. Y and Z. So here, what we have to define also is the parts, which is the ventricle wall, and the field function that we have to take is morpher entry. In the case of the x, it will be the x direction. For y, again the wall, and select the function morpher j, and again the same. Morpher entry. Okay, so take care to define everything good, but we will have these monitors already declared. And as one last step for this section, would be to create a new vector, which will be morph surface mesh entry, since this is what we're going to use, as I said, as the entry to a surface mesh operation. And this will be a vector which will be composed of the sum morpher entry I, sum j, and sum k. So with that, we can close this. And as I said, then we have to go to the region and specify the boundary condition for the moving wall. For that, the motion specification here in the ventricle has to be changed to morphing. Then in boundaries, we go to wall, and physics conditions, we have to change morpher specification to displacement, the morpher displacement specification to incremental, since we have done it in incremental. If you have done it in another way, you will have to choose this otherwise. And finally, we have to introduce the field function here as a field function, and it would be the morpher entry we created before. And with that, we have just prepared all of the things that we need for the wall movement. So going back to the slides, as you can see, we have finished with this. So the last step before initializing and running would be to do the meshing. And for that, as you can see, we have already created this automated mesh, but we can also define the different default controls to improve the meshing, and that way also improve the moving wall sequence, right? And apart from doing the automated mesh, we are also going to introduce a surface preparation for morphing, which is morph surface mesh. And then we're going to go back to Star-CCM, and we're going to create these operations and meshing. So before anything, we are going to clear the generated mesh. And here, as we already have declared the different measures, we already have done that, and we just have to change some default controls. I've chosen this. You can refine the mesh further if you need it. We know that for this case, this is sufficient. Then the volume growth rate, we have used the default one, 1.2. You can also modify this. Then in prism layer controls, we use 5 layers. So the adaptation of this has proven to us that it improves the adaptation of the wall to the mesh movement. And also we reduce this to 1000 from the relative size of the base. And we also like to do this 5 cycles with a threshold quality of 0.8. But well, this you can modify as you wish to create better meshes. And as I said, not only that, we're going to also use surface preparation. In our case, a morph surface mesh. Here we're going to introduce the part which is ventricle, the displacement which is morph surface mesh entry, and we will include just the wall boundary here. So now we have defined all of the meshing options we want. You can also include any other meshing or surface preparation thing you need. In our case, for these two is sufficient. So we're just going to click on generate mesh, and this way we're going to be creating the volumetric mesh in our left ventricle, the idealized left ventricle model. So now we have already declared the boundary conditions. We have already declared also the moving wall. We have done the meshing. So now the last part would be to define the methods and controls for the solver, initialize the solution, and finally run the simulation. So while this is meshing, we're going to go back to the slides and see this last part. So before we run the simulation, we will also specify some details on our methods and controls. For example, we will create the time step parameter and introduce it in our implicit and steady solver method. Then also in mesh morpher, we're going to check some specifications so as the morphing is more accurate and we repeat it each cycle. And we can also define some controls such as the CFD. Then we can also export some of the time steps of the velocity, the density, the pressure, or the vorticity, and using the automatic export. Then we can also fix the initial conditions using the continuous, as we mentioned earlier. And also we have to define some stopping criteria such as the inner iterations in each time step and also the maximum physical time. In our case, where you can also use maximum time steps, for example, but in our case, we will define the maximum physical time as 5 times the period. And well, finally, for running, we have to follow these 3 steps, which is first map the data, then initialize the solution, and then run. And every time we clear the solution or clear the mesh, restart this simulation, we have to do this sequence, map the data, then initialize, and then run. So let's go to Star-CCM. And as I said, well, we can close this. And as I said, we are going to go into the solvers. And here in implicit and steady, we are going to define, well, we previously defined the parameters, which are the time step and the time period and the period of the cycle. So we can go here and define this as the time step. We also use a second order temporal discretization. Then in the mesh morpher, we are going to check also the boxes that I showed, I described on the slides, which are these. And on the controls, we can also change this CFL control method to automatic and change, if it's necessary, these properties to have, in our case, one initial CFL of 1 and a maximum of 10. So once we have done this, we can go to the automatic export and here define the name of your file, of your directory, and then the scalar function that you want to extract, which in our case is density and pressure, the velocity and vorticity in the case of the vectors, and the regions would be Ventricle. On the boundaries, we can select all of the boundaries or neither. And the most important thing is to enable this update. The trigger, we have select the time step, and the frequency would be 20. So once we have done this, we can also go to continua, and as I said and mentioned earlier, here we can change the initial conditions. In our case, would be constant and 0 for both pressure and velocity, but well, you can change that if you need it. And the stopping criteria, where our inner iterations, we will define it as 30 in each time step. We will also change this logical rule to and we will do something similar for the maximum physical time, defining, for example, 5 periods of a Hertz cycle. And then we have the stopping criteria defined. And finally, as I said, what we need to do is first map the data, in our case using the surface data mapper, which we have used. Then we go to solution, we can initialize solution now, and finally run the simulation. So you will see here that the residuals start to appear, and the mesh is going to evolve, and well, you can also plot the scenes of velocity or plot the volume or whatever. So with this, we have prepared all of our simulations, and following this tutorial, you should be able to mimic these solutions of the curve criteria, vorticity, and velocity that we show here, and see the evolution of the vortex ring in the hard cycle. And well, thank you all for watching this tutorial. If you have any questions, you can look us up in our website and see the other codes and videos we have there. Also contact us if you have any feedback or any questions. And well, that was all for today. I hope that the tutorial was clear, that you were able to follow it. If not, you will also have the slides available, so you can follow it. And well, if you have any feedback or question, again, just contact us and we will try to solve them. Thank you all and have a good day.